In this video, we're going to continue on chapter 4 from where we left off on Monday, right? So let's take a look at the SR latch. Let's do a slight recap on the SR latch that we talked about on Monday. Now, so this is the block diagram of a SR latch, set reset latch. Now, so what happens here is that if I have my initial state of Q is 0 and Q bar is a 1. So at the moment set is 0, reset is 0. So what's going to happen here is that if I change set to a 1, right, then what will happen is Q bar will become a 0. Right? Then after that Q will become a 1, right? So this is what we mean when we set a SR latch. That means we set the output to be a 1, right? So what do we have here is that Q will become a 1 and Q bar will be a 0. So this is what we call the set mode. Now then what happens when we go into, what happens when now set is changed to 0. Now then this does not affect the output of Q, right? So when set and reset are both 0, right, we enter into a mode. Okay, so this one is same as the previous, right? So basically what happens is your Q and Q bar doesn't change when both set and reset are 0. So this is what we call the latch mode. Right now, so what happens is in the meantime, right, set can go back to 1, right? Set can go back to 1, then go back to 0, and it will not change the output of Q and Q bar. Now, then what happens now is that if reset is changed to a 1. So when that happens, then what is going to happen is Q will become 0, right? Q will become 0 and Q bar will become 1. So you have successfully reset the latch. If we have reset the Q to a 0, or we say that we can also say that now Q is equal to 0. We set Q to be 0. Okay, so this is in the reset mode. Now, when you are in the reset mode, right, when you're in the reset mode, when your reset changes back to 0, so what happens is that the output are not going to change, because when set and reset are both 0, we are in the latch mode, meaning that the outputs will not change. Now, the last mode that we have, the last operating mode that we have is when both inputs are 1, right? Then what will happen is then your output will become 0. Now this is an invalid state. Now why is this an invalid state? Because it will cause the next state, right, to be indeterminate. Okay, now so in summary, what a SR latch does is this. So let's say when the inputs are all 0, right? So we have a mode whereby whatever the output is, it will just remain as is. Okay, so now if I set, meaning that I'm going to change the set input to a 1, then I'm going to store a 1, right, in the output Q, right? Then Q bar will become a 0. Now after that, if my set goes back to 0, right, my output will still be stored there. So we enter the latch mode. Now in the meantime, the set can switch from 0 to 1, 0 to 1. It does not matter, right? The output will remain as is. Okay, until the reset signal is set to a 1, right? When your set is a 0, and that you go into the reset mode, the output changes. Okay, the output goes to a 0 and the Q bar becomes a 1. Now then the final mode is the invalid mode, when both S and R are 1 at the same time. Okay, and you will cause the next state to be indeterminate. So this is the basic function of a latch. Now then we talk about a gated SR latch, whereby we add AND gates or NAND gates so that we control when we want the latch to work. At this point, we will move on to the second type of gated latch, which is the gated D latch. So now, if you look closely, right, this latch has a very big difference compared to the one previously, right? The one previously, right, you do not have the D here, it is just the set and reset. If you look at this latch, it is called a gated D latch, right? So it's called a gated D latch. So there are no set and reset inputs. Okay, so there is only one single input D, right? So this one single input D, you can see that when D goes to the NAND gate, right, then the D bar will go to the second NAND gate. Basically, what happens here is that you are trying to implement the set and reset, right, with the D and D bar. The enable again is to enable the the latch, right, whether to enable it or whether to disable it. Okay, so this is addressing an issue that with the SR latch, because SR latch, right, there is an invalid state, right? So this one actually helps to address that issue, right? So with the SR latch and the gated SR latch, right? So by having the D and D bar, right? So these two inputs will not be one at the same time. Okay, so let's take a look at how a gated D latch will work. Now let's take a look at the timing. Right, what we have here is a block diagram of the gated D latch. So you have the enable and you have the D. So the set and reset is actually condensed into one control with the D, right? So imagine that your enable is a 1, right? So when D equals to a 1, then you are doing a set action, and when D equals to a 0, you are doing a reset action. Okay, now so let's take a look at the timing diagram. Now, if you look at the timing diagram, right, what you need to focus on is when the latch is enabled. So when the enable is equals to 1, then it's going to the latch will be active. Okay, so take note, only when enable is equals to a 1, right, then your latch will be active or enabled, right? When enable equals to 0, then your gated D latch will always be in the latch mode, right? Nothing will change, the output will not change. Okay, so please take note of that. So whatever that we have here, you just need to focus on the enable equals to 1. So let's take a look at the example over here. So say that my Q was initially at 0 and Q bar was at 1. So what happens here is in this part here, because enable is equals to a 1, so when D goes high, when D goes to a 1, so you are entering what we call a set mode. Right? So your Q goes up to a 1. Now then what happens here is while it is still enabled, right, D goes to a 0. So you are going into what we call the reset mode. Then after that, continue. So you continue. So up to this point is Q will still be having output 0. Now on the other hand, Q bar is going to toggle to 0. Then when Q equals to 0, then Q bar becomes a 1. Now then what happens here is at the next instant, right, when D is equals to a 1, you realize that because enable is equals to a 0, right, so there will be no change. Okay, there will be no change here. Right, so when enable equals to a 1, right, this is when the Q will actually follow what D is, right? And when enable is equals to a 0, there is no change in the output, right? Even when D goes to 1. So when D goes to 1, right, no changes to the output, right? Because your latch is not enabled. So this is going to continue to be at 0. Right, all the way until now when your enable goes up to a 1 again. Okay, and what happens is D goes up, right? So you go into the set mode again, right? Q equals to a 1. Then after that, when the latch is still enabled, Q drops to 0, right? Then your output also drops to 0. Now then I'm going to complete the diagram for the Q bar, which is the exact opposite of what Q is. Right, so this is how a gated D latch works. So to give a simple statement as to how this gated D latch works, so you can say that when enable is 1 or when the latch is enabled, basically Q will follow what the input D will be. Okay, so when the latch is enabled, when the gated D latch is enabled, when the gated D latch is enabled, right? So your output Q will just follow what D is, right? So you can see at this moment, D is equals to 1, then at this moment, then Q equals to 1, when D equals to 0, Q equals to 0. Now obviously there will be a time lag here, okay, because there is the processing that has to go through, right? Is going to go through the NAND gates and also the NOT gate. So there will be a slight propagation delay between the Q and the D. But at this point of time, right, we are not considering the delay yet. So we just say that, okay, imagine that the response is immediate. Okay, so in future when we talk about there's a finite propagation delay, then we are going to say that, oh, there will be a slight delay here. The Q will actually rise up to a 1 with some propagation delay. Now we are done with gated D latch, right? So we have completed the section on gated latch. So we have the gated SR latch and gated D latch. Now moving on, right? Then we come to the point that having a D latch, it may not be a perfect solution for synchronization. Now what do I mean by synchronization? Now when it comes to synchronization, we are always talking about a clock, right? Okay, will the changes be synchronized with the clock pulses? Okay, when the clock goes from high to low or low to high, right? So what we want to do now, right, is actually to have a latch to be enabled, okay, when the clock goes from low to high. So take note, so what we want now, right, is a latch to be enabled when the clock goes from low to high or from high to low, depending on which you want, which type you want. Okay, so you want the latch to be enabled only when clock goes from low to high. So what you want here, right, is a edge detection circuit. So maybe let me draw the pulse that we want. So basically when clock goes from low to high, or when clock goes from high to low, now we want the latch to be enabled during this part here, right? So we want the latch to be enabled here. Then after that, don't care already, right? The moment that after this from low to high or high to low, then we do not want the latch to be doing any work or to be making any change. So we only want the latch to be enabled only when the clock goes from low to high or high to low. So what we need here is a edge detection circuit, right? Now then there are two types of detection that we want. The first type is the low going to high. So this is what we call the positive going transition. That means we want to go from low to high, okay? Or we want to detect a high to low, right? So that will be the negative going transition, right? From a high to low. Now, so we need to think about an edge detection circuit. And to do that, right, it is actually quite a simple circuit here, right? Basically what you need is a NOT gate, connected to an AND gate. Now, so what we have here, right, is same clock signal, right? The same clock signal that we have, that we were talking about just now, the same clock circuit to be connected. Now, one to the AND gate, and the other one of the AND input, right? We are going to put the clock to go through a NOT gate, right? Then go to the input. Now, on the surface, it seems that the output of this AND gate will never be a 1 because the input here and here will always be opposite. Okay, but let's just take a little while to think about how all these gates work. Now, inside these gates are actually transistors, which require some time to process the signal. Maybe in a matter of maybe microseconds. So there will be a time delay for this NOT gate to respond. Okay, so example, now imagine that your clock is a 0. Let's say imagine that the clock is a 0. So this is the initial state. When clock is a 0, then the output of the NOT gate here will be a 1 and the output will be a 0. Okay, this is simple. Now what we are doing here is we are going to transition the clock from 0 to 1, okay, the transition from 0 to 1. Now take note that all gates here, right, will require a finite time to process the signal. Okay, it may be a very short time, but there is still a finite time there, right? So imagine that clock now changes to a 1, right? So now clock becomes a 1. Now take note, at that moment, right, at that moment when clock becomes a 1, the output of the NOT gate has not changed yet because it requires a little bit of time. So we are talking about that little moment there when the gate of the NOT has not changed yet. Okay, when the gate of the NOT has when the NOT gate has not changed its output yet, so the output is still a 1 for that little moment. Okay, maybe let me write down some description here. The NOT gate takes a short time to process, and we call that a propagation delay. So the output still at 1. Now for this little moment here, when both inputs of the AND gate is a 1, right, then my output will become a 1. But we have to understand that this is only for a very short moment. So that's why we call this momentarily 1. The output is 1 for just a very short moment, right? So final, after maybe some microseconds or maybe some milliseconds, then the output of the NOT gate becomes a 0, and then this one goes back to a 0. Now, so what is the purpose here, right? You realize that you actually enabled, right? You enabled the AND gate here for that little moment, and this is the edge detection circuit that we want, right? So let's take a look at how the clock and the X, which is the output of this, let's call this output X. So what we want to do here is we want to trace how the X output will respond. Okay. So when clock goes from, when clock is 0, then the X is 0. Let's draw that up first. Now then when clock goes up to a 1, so what happens here is that, right, there will be one moment when the NOT gate has not changed state yet. When clock is a 1, that the output is a 1. So that little moment, there will be one short moment whereby the output X is equals to a 1. Okay, then after that propagation delay of the NOT gate, the output of the NOT gate becomes a 0 and the output of X becomes a 0. So this is how it looks like. Okay, so then after that, no changes here until the next clock transition from 0 to 1, right? Then the X goes up again and comes down in a short while, which is pretty much equivalent to the propagation delay of the NOT gate. Similarly here, right? So what we have here, right, is a very short spike, right? You can call this a momentary spike, and it is during this short moment that your AND gate will be a 1, and that AND gate will be connected to will be used as the enable, will replace the enable that we had previously, right? So now let's take a look at how we incorporate this circuit, right, into the okay. Now so at this point I also want to add on the transition. Basically what happens is all this momentary spike is when the clock signal goes from 0 to 1. Now, so what do we have here? We talk about latches. Latches are what we call level triggered. So when set goes to a 1, then your Q becomes a 1. Then when reset goes to a 1, when set is a 0, then you reset your latch. By the is level triggered and is asynchronous. Means it can happen anytime, right? So when reset is 0 and set is 1, right? Then at once past the propagation delay, then your output will change accordingly, and this can happen anytime. Now, so what happens here is we introduce the gated circuits where we have an enable signal going to control when the latch is active. Now, So now what we have come up with, right, is that we have created another circuit which is to have a edge detection circuit to enable the latch. So we don't no longer call that a latch, we call that a flip-flop. So a flip-flop is only enabled at clock edges, right? And it can be positive edge triggered, meaning that when your clock goes from a low to high, right? So this is what we call a positive edge triggered, or you can also have a negative edge triggered. Okay, when your signal of the clock goes from high to low, and we are basically using the edge detection circuit that we came up with just now to enable, okay, to enable the flip-flops. And so that's why we say that flip-flops are clock edge triggered. Only at that edge it is triggered, right? Only at that edge it is latched. That's why we changed the name. Now it's called flip-flops, right? When it is edge triggered. So please take note, latches are lever triggered and they can happen at any time. Flip-flops are edge triggered, okay, and they are enabled by the clock edge. And the two types of it is the positive edge triggered or the negative edge triggered, right? So this is the first flip-flop circuit that we are looking at. This is what we call the D flip-flop. Now, the name clock D latch, right, is a very loose name for the D flip-flop. The proper name for this is a D flip-flop because this is clock edge triggered. This is no longer lever triggered. Right, so rightfully, this is a very, very loose name for the D flip-flop. Now, so let's take a look at how we can analyze how this D flip-flop works. Now, because this is clock edge triggered. So because there is no bubble here, right, that means this is triggered when the clock goes from low to high, right? If you have a bubble in front of the clock, right, so you are going to be having a high to low transition. Okay, when there is a high to low transition, then your flip-flop is enabled. Now, so how do we actually analyze this circuit? Okay, so because this is clock edge triggered and because this is positive going transition, right? So it's going to be triggered only when the clock goes from low to high. So we are going to look at the clock signal. So we ignore the D first. Let's go to the clock signal. Let's look for all those places whereby you have a low to high transition, and let's highlight those places. Okay, so these are where you have the low to high transitions, and at these points, right, the D flip-flop is enabled. Okay, so now let's take a look at then we can look at what the output will be. Now, say that the Q starts from a 0. At the moment where the clock goes from a 0 to high, now let's say that the D is already a 1 at that point, so your Q actually goes up to a 1. Okay, and when does it now after it goes up to a 1, at the rest of this time, right, from here to here, right, the Q will not change state. Okay, it will not change state because at that moment your flip-flop is latched. Okay, it will only take action at the next positive going transition or the next low to high transition. So nothing is going to happen to the Q until the next low to high transition. Okay, so take note, there will be no changes to the output from this point onwards. Okay, there will be only a transition at the very beginning. Now, rightfully, to take care of propagation time and so on and so forth, right? Usually the D needs to be at high, okay, when the clock edge goes up. Okay, so rightfully the D should be ready at 1 when the clock goes up. Okay, right, so but for simplicity, we are just saying that when the clock edge goes up, the D is at 1. So let's continue to the next decision point. So at the next moment where the clock is going from low to high is when the D flip-flop is enabled. Okay, so at this moment D goes to a 0, so what happens to your Q? It will go to a 0. So you reset the flip-flop. Then again, same thing for the rest of the clock cycle, right? It is going to be a 0 until the next the positive going transition. And at that moment, let's look at what D is. D is a 1, right? So you go into the set mode, right? So Q becomes a 1 again. And this is going to be a 1 until the next PGT. At the next PGT, then you look at what D is. D is a 0, so it's going to go into a reset mode. Right, then let's go to the next next transition again. Next transition here, D is a 0, so your output will continue to be a 0. Okay, next positive going transition, D is 0, so Q continues to be a 0. Right. Now, what do you notice here is that at these points, right, at this point and at this point, you can see that D changes. D goes from 1 to 0, but because at this part, right, at this portion, right, the clock does not have any low to high transition, right, and at this moment after the transition, the entire time interval here before the next transition, right, your flip-flop is actually being latched. So even when your D drops to a 0, nothing happens here, right? So we can say that there will be no output changes, okay, at this part and at this part. Okay, same here. You can see that D goes up, but nothing happens until the next positive going transition, right? So you can see that everything that happens for the Q will be happening at the when the clock goes from low to high, right? If there's going to be any action, whether there's going to be any output changes, it will be at the positive going transition, right? So let's summarize the D flip-flop, right, using a simple truth table here. Now, so what we are doing here now is that we are going to put the truth table. Now, this is the input now, right, and this is the enabling mechanism. So when the clock goes from a low to high, you can see go from a low to high, and at that moment, if your D equal to 0, then at the next clock cycle, or we can say that at the output, right, will then becomes a 0. Okay, then at the rising cycle, when the we can say that this is the next state. Okay, this is the next state. Now, in actual application, right, there will be a time delay between. Now, example, let's say this is the D signal and this is your clock, right? This is your clock transition. Okay, so at this point of time, what will happen? Now, what happens is your Q, there will be a finite time for the flip-flop to process before it goes high. So this is the propagation delay, right? The delay, right, due to the circuit, right? The transistors that's operating behind. Right now, in the previous timing diagram, we have reduced this to 0, right, to simplify things, right? So, but in actual fact, there will be a small time delay, and that small time delay, right, will become very sensitive when your clock signal frequency is very high. Because when your clock signal frequency is very high, the period short, and when the period is very short, the propagation delay might interfere with this, and it might cause some synchronization issue, right? So please take note of that. So we have simplified things such a way that the Q actually transition at the edge, but in reality there will be a short delay. Okay. Now then, when at the rising cycle, when the D input is a 1, then the Q at the next moment, right, when after the propagation delay, right, is going to be a 1, right? Okay, so let's move on to the other features of flip-flops, right? Then for flip-flops, right, we also have preset and clear, right? So meaning that I can preset or clear a flip-flop. Preset means that I'm going to set the output Q to be a 1. So guys, I think I need you to put in some things that I missed out in the previous slide. Yeah? So please put the bar on top of the preset. So when bar pre equals to 0, we enter something called the preset mode. What does a preset mode does is we set Q to be 1, right? And when bar clear is a 0, we go into a clear mode. And what does that do? Okay, we are setting Q to be a 0. Right now, this is very, very useful, okay, when we want to do counters. But I'm going to talk about that later. So just bear in mind that there are actually two different functions here, or two different addition to the circuit, to the flip-flop, that is used to control, right, the presetting and the clearing of the flip-flop. Okay, and these are very, very useful features. Okay, so let's talk a little bit about flip-flops. Okay, I have not talked about the JK flip-flop yet. We are going to talk about that in a short while. Right? JK flip-flops, they are very, very useful as to be used in registers, counters, event detectors, and frequency dividers. Now, what are all these all about? We are going to talk a little bit about in a short while. So, ripple counters are actually quite easy to understand. So, what are registers? What are event detectors? All right, these maybe we'll when it comes, we are going to talk a little bit more about it. Frequency divider is quite easy to understand as well. So, ripple counter and frequency dividers, right? These are easy to understand. For the other two, we are going to talk about later. Right now, JK flip-flop, right? These are what we call universal programmable flip-flops. I'm going to show you in a short while what this JK flip-flop and how it works. Now, before that, right, I will first have to go back to explaining to you what a JK latch is all about. Previously, what we have done is only the SR latch, then the D latch. We have not gone to any other latches. So we are introducing something called the JK latch, right? And this JK latch, you will realize that you will be able to solve the problem of invalid state, right? Let's go to the JK latch. Now, if you look at the design of the JK latch, right, you will realize that there will be feedback loops. Previously, your SR latch doesn't have this feedback loop. It only whatever that you have for the SR latch is basically just maybe this part here without, right? Let me finish this part first, right? So this is how your SR latch, the NOR version, look like. Okay, so what have we done here is that we have added an additional AND gate in front, and then after that, right, we have a feedback loop. So this is what we call a JK latch, and this JK latch makes it very, very useful, right, when we want to take care of the invalid state. Okay, we are going to talk about that in a short while. Now, so what is the purpose of the JK latch, right? As I mentioned, is to resolve the problem of invalid states that we had in the NAND or the NOR SR latch. Right, so what we have here is by looking at the circuit, you can see that Q is being feedback here and Q bar is being feedback here. Right, so previously this was the set and this was the set and this was the reset. So let's put it down. So this was the set and this was the reset, right, previously. Now, so what does a JK latch do, right? It is going to eliminate the possibility of Q and Q bar to have the same value at the, okay, it will remove that possibility of Q and Q bar having the same value. Then when J is equals to 1 and K equals to 1 on the next clock, what happens is the Q output will be the complement, right, of the current Q output, right? So there are going to be two versions here. This is the NOR version and this is the NAND version, right? So let me finish by writing. Now the set and reset is based on the previous SR latch, the NOR version and the NAND version. Now I'm going to go through how a JK latch works, right? So let's talk about how a JK latch works. Now in the next slide here, so this whole slide is talking about how a JK latch works. Now, so what we are going to do is we are going to start off with putting in some initial conditions. Say that initially, right, Q equals to 0 and Q bar equals to a 1. Right, say this is a 0 and this is a 1. Right, so initially these are zeros. Now at this moment, what is going to happen is my J is now changed to a 1. Right, so let's see what will happen. So please follow this closely because I'm going to do all the changes in one diagram. Okay, now so when J is equals to a 1, right, when J equals to a 1, so what is going to happen here is you will still have to depend on what the output Q bar is. So don't forget that this is the set and this is the reset. Right, so when Q bar is equals to 1, so let's take a look here. Then I'm going to feed back a 1 here. And this is going to be, now set will now be equals to a 1. Now at the moment when set becomes a 1, and we know a NOR gate, right? A NOR gate will become, the output will become 0 the moment any of these input is a 1. Right, so at the moment when set becomes a 1, the output here changes to a 0. Means now my Q bar will become a 0. Right, Q bar will become a 0. Okay, then let's take a look here. Now the Q, which is a 0, is being feedback here. Right, so reset is a 0. Right, now then when this 0 is coming to here, then when both inputs of the NOR gate is zeros, right, then my Q becomes a 1, right? So this one becomes a 1, right? So we're actually setting, right? We're actually setting the JK latch when J equals to 1 and K equals 0. Now, so this is as per usual. Now, of course, when the Q goes back to this, your reset doesn't change here because when if the Q equals to 1, this is the AND gate. Right, so this is still going to remain as 0. Right, so this is the initial settings. Right, so now what we are going to do is we are going to look at the situation when J equals to 0 and K equal to 0. Now again, I'm going to do a sequence of changes over here. So please take note, right? So please take note of what is going on, right? Now, so when J equals to 0, so just now we have set the Q to be a 1 and Q bar to be a 0, right? So now imagine that both your J equals 0 and K equals 0, right? So this is equal to 0, this is equal to 0, okay? So let's take a look at what will happen here. Now, the output here is feedback to the AND gate, the input. So the set is put to a 0. Right, so right, then what do we have here is then the Q is a 1 here, right? So the reset is also a 0, right? The reset is also a 0, right? Now the output Q bar is going to go up, and when the two inputs are both zeros, the output will remain as 1, right? And the 1 that is feedback to here, right, will ensure that the output here will be a 0, right? So so we are now in the latch mode, right? So nothing changes to the output, right, when J equals to 0 and K equals 0. So up to this point, right, the JK latch doesn't really look much different from the SR latch, right? But the moment when you have J equals to 1 and K equals to 1, if you still recall, SR latch will give me both outputs to be 0, and then the next state will be will not be able to be determined, and that is going to be a problem. Now, so we are going to look at the J equals to 1, K equals to 1 situation for a JK latch, and let's see whether it solves the problem of the output being indeterminate, right, for the SR latch. So let's take a look at the j equals to 1, k equals to 1 situation. Okay, remembering that we had the q equals to 1 and q bar equals to 0. Right, so at this point, so what's going to happen is we set j and k to 1, right, at the same time, right? And this is an invalid state for SR latch. So be mindful of that. Huh? So it's an invalid state. Now, so what's going to happen here is we are going to then, whatever output that comes from here, for okay, this will be my reset, and this is my set because this is the null version, right? Let's see what will happen. Huh? Okay, the feedback here, this is a 1, and this is a 0, right? So it becomes my reset is a 1 and set is a 0. Now, when reset is a 1, right? So regardless of what the other side is, the output will become a 0. This is, right, this is for a NOR gate. So take note, NOR gate, when any of the inputs is a 1, the output will be a 0. Okay, now so what you have seen here is then your Q becomes a 0. When the 0 is then feedback to the input of the NOR gate, then we will have a 1 at the output here because both inputs are 0. So now your Q bar becomes a 1. If you look at this, we don't have a situation whereby Q and Q bar are both. What you have done here, right, is that when the Q is a 1, it becomes a 0. When the Q bar is a 0, it becomes a 1. Right now, so what we have done here is we have switched the Q and Q bar when j equals to 1 and k equals to 1. So you did not enter into an invalid state. So what happened is the output just from 1 becomes to 0 and from 0 becomes to 1. Now, I'm going to do one more cycle, okay, based on j equals to 1 and k equals to 1. Now that my output has changed to 0 here and changed to 1. So imagine that my input here is still 1 and 1. So what happens to the flip-flop, right? So let's do the thing again. Now, if you are fast, you know that the output will just switch again. But let's just go through this, okay? So same thing, we are going to feedback the Q, right, to the input here. The Q is a 0 and the Q bar is a 1, right? So set is a 1, reset is a 0. And so again, when any of the input, right, is a 1, then my output becomes a 0, right? So my Q bar becomes a 0, right? And when that 0 is being feedback to the input of the upper NOR, both inputs are 0, right? Then my output becomes a 1, right? So what you have here, right, is that when j equals to 1 and k equals to 1, the output, right, will toggle, output will toggle, right? So you will toggle between 0 and 1, then from 1 to go to 0, then after that you go to from 0 to 1. So you will just keep on switching repeatedly. Okay, so what you will see, right, if this is just a JK latch, right, is that the output will just keep on going from 0 to 1, 1 to 0, 0 to 1, 1 to 0 repeatedly, right? So your output will switch repeatedly, right, between 0 and 1, okay, so long as j equals to 1 and k equals to 1. Right, so you will not get into the invalid mode of the SR latch. Right, so let's make this JK latch even more useful. And what do we want to add on? We want to change it to edge detection circuit. We want it to be enabled with the clock. We are going to make a JK flip-flop. Right, so this is going to make the circuit right, to be able to be controlled by the clock signal. Right, so what do we have here is the JK flip-flop. Now, so let's break down the circuit here, right? So what do we have in the first part here is the clock detection circuit. So basically this is just a clock going to a AND gate, then clock goes to inverter, go to the second input of AND gate. So what you have here, right, is the output here will be a single momentary spike, right, when clock goes from low to high. Okay, so this is the edge detection circuit, and when you detect a edge, then it's going to create a spike to enable the flip-flop. Okay, and this is a JK latch, right? This is a JK latch with a enable that comes from the edge detection circuit, right? So you have a JK latch. This is the JK latch. You have the clock, then the edge detection circuit, and with the enable. So if you look at this, this is the enable, right? So this is your set, this is your reset, okay? And the feedback here makes it a JK latch, right? So this whole item here is what we call a JK flip-flop, and this is one of the most versatile flip-flops, and this flip-flop is going to let us be able to use this flip-flop to imitate many different flip-flops. We're going to talk about that in a short while, right? But what we are saying here is that we have a JK flip-flop which is positive edge triggered, right, from this circuit here. So there will be a pulse, there will be a momentary spike or pulse which will enable the JK latch or the JK flip-flop, right, when it goes high for that moment. Okay, and when J equals to 1, K equals to 1, what will happen is the output will just switch. But if it's a 1, it will become a 0. When this is a 0, it becomes a 1, and vice versa. Right, so what we are going to do is we are going to use a timing diagram, right, to demonstrate how a JK flip-flop actually works. Okay, so we have the JK flip-flop diagram here. Now this is, right, quite a bit of circuit that we have here. So if you break it into 3 parts here, this is the clock, right, or the edge detection circuit. This is the enable, right? Then after that, this is your JK latch, right? If you break it down this way, it is going to be a lot easier to see, right? So 3 parts here, clock detection, enable, set reset, JK latch. So the whole thing here is that we will need to look for where you need to make a decision, and this decision point will be made at the positive going transition of the clock. So at this point, this is when, right, at these points, these are, so let's put the arrow here, is when you enable the flip-flop, right? So we are only going to focus at any of the actions that's going to happen at these locations. Okay? And at all other moments, right, then your flip-flop is going to be in the latch mode, right? So let's take a look at this. When clock goes high, right, then the first thing to look at is to look for the J or the K. Now in this case, you can see that when during this momentary pulse, when clock goes from 0 to high, your J is a 1 and your K is a 0, right? So imagine that Q is start from 0, you go into the set mode. So at this moment here, you do a set, and whatever that you have for Q is going to remain the same until the next clock, okay, until the next positive going transition. Right now at the next positive going transition, J equals to 0, K equals to a 1. So you do a reset. Now take note that reset is right at the clock edge. Okay, so there'll be a reset here, right? Then for the rest of the clock cycle, nothing is going to happen. Now you realize that all these changes, right, in the J and the K, there is no action here. You can see. Let me, right, there will be no action here, right? Because it is only at the clock edge, right, then your flip-flop is enabled. So even though K becomes a 1 earlier, it is not going to change the output, and it will only change the output at the next clock cycle. Right, so going to the next clock cycle, J equals to 1, K equals to 0, you are going to set mode again. Now, again, this is going to continue until the next clock cycle. Now, this is the part that you need to be very, very careful about, because at this moment, you can see that both J and K is 1. Right? So when J is equals to 1 and K equals to 1, right, you go into something called the toggle mode. That means your Q is going to switch from 0 to 1 or 1 to 0, right, depending on what state it is. So because Q is at a state of 1 previously, right, so at the moment when the clock cycle goes up, right, when clock goes from low to high and J is 1, K is 1, the output here will change state. It will change from 1 to 0 or 0 to 1. So because Q is a 1, so it will change to a 0, right? And what mode is this called? This is the toggle mode. Right, then at the next clock cycle, now of course when I look at this drawing, right, the J and K needs to be a 1 before the clock cycle. So rightfully I should draw the J to be a 1 and K to be a 1 slightly earlier. Okay, so at this point of time, you go into a toggle mode again, and my Q is going to go up to a 1. It will change from a 0 to 1, right? Then until the next clock cycle. Now at the next clock cycle, you realize that J equals to 0, K equals to 0. You go into the latch mode. Okay, so no change. Okay, latch or hold, right? So there will be no change in your Q, right? Quite a bit to digest here, right? So what do we have for Q bar? Now, because now you don't have an invalid state, right? So whatever that you have Q and Q bar, they will always be the reverse of each other, right? So when Q equals 0, Q bar will be a 1. And when Q equals to 1, Q bar will be a 0. So the Q and Q bar will be the exact opposite of each other, right? So this is how a JK flip-flop works. So it solves all the problem that comes with the SR latch. Okay, so when J equals to 1, K equals to 1, you go into the toggling mode. Your Q just keep on changing, switching. Okay, so what do we have here for the truth table is this. On the positive going up clock cycle, right, when J is 1, K is 0, okay, we go into the set mode. The next Q is 1. Now when we say the next Q, we are saying that after the propagation delay, right? So if there is no propagation delay, then you can say that at the same clock cycle, your Q becomes a 1. But as I mentioned before, practically there will be a short time delay. Okay, and when J equals to 0 and K equals to 1 on the positive going transition, your Q is going to become 0 right after a short propagation delay. So this is in the reset mode. Now then, if J is 0, K is equals 0, the next Q will just be equals to the previous Q, right? Or we call this the latch or the no change. Okay, there'll be no change in the output. Okay, and the last one, which used to be an invalid state for the SR latch, right? Then when J equals to 1, K equals to 1, then whatever Q is, it will just become Q bar, right? So we are in the toggle mode. Right, now, so at all other time during the clock cycle, right, at all other time of the clock cycle, right, then Q is just going to remain. There will be no change. You can call it the latch or the no change mode. Right, so this is for the JK flip-flop. Okay, then now once you have the JK flip-flop, then right, some engineers thought that you can also simplify the JK flip-flop, right? If you just want the flip-flop to keep changing state, right? There are some use for this, right? So we're going to talk about the use for this later. But what we have done here is we have connected the J and the K together, right? Both the J and K inputs are connected together. Now, if you realize this is the same as J equals to 1, K equals to 1, which is the same as the toggling mode. So that's why we call this the toggle flip-flop, right? So when T is equals to 1, the outputs are toggling between 0 and 1 continuous. Okay, so the difference between the JK flip-flop and the T flip-flop is that instead of having a J and a K here, we have combined the two inputs to just a T input. Right, so this flip-flop, okay, what it does is when t equals to 1, it will just keep toggling the output, right? The truth table for a t flip-flop is very simple, right? When t equals to 1 on the next clock, the next output will be the complement, right, of the current Q. So okay, when on the uprising cycle, when t equals 0, right, then your next Q will just be the same as the current Q. If the t equals to 1, then you will toggle. Okay, so this is the t flip-flop. Right. There are some more materials on the next slide which I will cover again during lecture. Right. At this moment, what I need to do here, right, is that I will be recording another video on one short application on registers because you need that for the lab. So we will now jump to the part on registers which we will need for the lab that you're going to do on week number 8.